All right, hello everybody. My name is Derek Demeter, Planetarium Director at the Emil Buehler Planetarium in Sanford, Florida at Seminole State College. We have a special guest with us tonight. That is Dr. Mark Subbarao. He's from the Adler Planetarium. He's going to tell you all about what he does with the facility and all the cool things that he's going to show you tonight. And of course, you know Justin Cirillo, our planetarium specialist. He's going to be with us, and he's going to be helping us out throughout tonight's program. And so tonight we're going to be talking about climate science. This is Earth Day was just yesterday, 50th anniversary of Earth Day. I honestly think that Earth is the coolest planet in the solar system, but I'm a little biased on it. But then again, we have everything we want, everything we need on Earth. And even though we're kind of going through a hard time right now, Earth is still a really great place to be. But so what we're going to do is we're going to talk a little bit about some of the things that are happening in our world today, and how we as planetarium professionals, how we can actually express and educate climate science and data through the use of planetarium technology. And so what better person to talk about that than Mark Subbarao with his work at Adler. So Mark, can you go a little bit in detail about who you are, what you do, and all that jazz?
Yeah, I'm happy to. Thanks so much, Derek. And really, thank you so much for inviting me to be part of tonight. My background's as an astronomer. I study galaxies. And really not just galaxies, but how galaxies are distributed in space. So one thing I found, especially as I've gotten older, is that I've started to realize that, the distant universe is great, but I want to do, things that matter here on Earth are really important. So one thing that I started doing a couple of years ago was think like, our work in the planetarium, a lot of it's focused on stuff that's pretty remote, but really trying to look at what can we do to talk about things that really matter for people here on Earth. And of course, as we're all going through this pretty serious global issue right now, there's a nice perspective that you get from looking at the Earth as a planet and looking at it in context with the rest of the universe. And I think that's something that we as planetarians can bring to the whole climate change education.
And of course, Mark wears another hat as well. He is the president of the International Planetarium Society. So again, we really appreciate you joining us this evening, Mark. And what we're going to do is we're kind of break it up into a two-parter kind of thing. The first part, I'll be going a little bit about kind of the history of how we explore climate history, not just what's happening today, but how we've explored climate and for a very, very long period of time. And we're going to be utilizing some of our software. But Mark has some really cool data visualizations that he's created that he's going to show using his version of the same software that we're using on his computer later on in the program. And of course, as you all know, for our previous shows and our programs, Justin will be monitoring the chat window or the Facebook Live page. So if you have a question that you want answered, be sure to let him know, and Justin will do his best to let everybody get a chance to chime in on those questions. So are you all ready to get started with our public show? All right, let's do this. Okay, so I'm going to go ahead and start sharing my version of the program first. So so basically, this show is called 2 degrees because climate scientists believe that 2 degrees is the temperature which it's kind of the point of no return for climate science. Once you get past that point, things start to get really, really, really crazy real fast. And so we're in this time period now where we're still not at that point yet, but we could very likely reach that point. And that's how, and we tackle some of the things that we just now. Believe it or not, historically, the Earth has been warmer than it is today. In fact, it's actually the hottest that we've really recorded is over 8 degrees warmer. But the world was a lot different back then, and talking about how that affects. And of course, the most important thing with climate is that we enjoy Earth the way it is right now. And if we speed things up too fast, we're not going to be able to catch up with it. And even though climate does happen naturally, it takes a lot longer than what we're noticing with the climate trends today. So, of course, the most important thing is we need to look at the recipe for climate. Climate's very difficult. It's not like weather. It's not like meteorology where you can just look at a couple of days and kind of see how things are going. We got to look at very long time scales. And there's a lot to climate science than just, just a few things. There's actually a lot of different things that contribute to climate, but there's one element of the recipe that has changed over the last billions of years, and that, of course, is humanity. Humanity is adding an extra piece of that recipe, and that's what Mark will be talking about a lot later on in his part of the program. So as I said, we're going to talk a little about the climate for recipe, and what I'm going to do here is I'm going to stop sharing my screen, and we're actually going to go head over to our Uniview computer here. So what I'm going to do here is I'm going to start sharing our Uniview space here. So as you can see right now, we are right flying around Earth, if you will. And again, our planet is a special place. We orbit the sun about 93 million miles, which is, on average, pretty good. We live in the Goldilocks zone. We live in a habitable zone where liquid water is prevalent. The temperatures are nice. For the conditions of life. This is very, very important when dealing with climate. Venus is way too hot. By the way, you can see Venus in the sky up at night in the west. So after sunset, look to the west, you'll see Venus. Venus is what you don't want happen to Earth. It got way too hot, and Venus is inhabitable. Same thing happened with Mars on the opposite spectrum. Mars lost its atmosphere, the climate cooled dramatically. So you can have global warming and you have the global cooling, and both of those things don't really work very well for you. But the Earth, though, does go through these various different cycles that are affected primarily through the Earth's orbit, the amount of sun output, and all these different things actually have an effect on our Earth's climate. The weather patterns, high pressure systems, all these things over the course of millions and millions of years can affect the trend in climate. So what we're going to do right now is we're going to go ahead and zoom out real quickly here, and we're going to take a look at Earth's orbit. Now, as I said before, the Earth goes through, we orbit around the sun. It takes 365 days to do that. However, Earth's orbit is not completely circular. It's actually a little bit more oval shaped, not too much. Earth's orbit is fairly circular, but essentially our Earth's orbit is, and I'm going to go ahead and turn off the orbits of the other planets so we can really see just Earth's orbit in there, and we'll get rid of Pluto as well in the background. So you can see there's Earth's orbit, and as you can see, Earth's orbit is fairly circular for the most part. And being that it's nice and fairly circular, we tend to have a very pretty good climate exchange. However, because we have planets that are orbiting around us and things like that, pass-bys of asteroids, the Earth does kind of wobble in its orbit a little bit, and we get a little bit of what we call eccentricity. Basically, it's where the Earth's orbit is a little bit less circular and a little bit more egg or oval shaped. And there are times in which the Earth is actually closer to the sun and farther from the sun. We call that perihelion and aphelion. And perihelion means that we're closest to the sun, and aphelion means that we are farther from the sun. And believe it or not, you might think to yourself, if you're a person that lives in the northern hemisphere, we're actually closer to the sun in July. So, of course, when you think of logic, for those that live in the northern hemisphere, we're actually closer to the sun during our summer and farther from in our winter. But that isn't the case with the southern hemisphere. They have the opposite seasons. But remember, over 26,000 years, our Earth does wobble around. So believe it or not, our Earth does this. Our Earth kind of wobbles around kind of like a top. And over 26,000 years, the seasons shift and change. Well, if you add the shifting of the Earth's seasons over time, you also affect the position that the Earth is in around the sun. This is going to deviate the temperatures and changes and fluctuations over time, which actually slowly compound and adjust the climate. Now remember, this takes millions and millions of years. for any gradual change. And there's a cycle called the Milankovitch cycle, and we'll actually show you the graphs of that and how for the last 500 million years things have been fairly steady. But we're starting to see a different change that's happening today. And so the Earth does go through natural climate changes. We get colder, we get warmer, and not only is the Earth's orbit affect our climate, the sun affects our climate. Right now, we live in a solar minimum. That means that the sun's output is not that strong right now. It's not shooting off these massive energetic flares as normally as it does when it's at solar maximum. There's not as many sunspots. There's not as much violence going on in the sun. And when that happens, the sun actually gives off more energy. And so we actually can warm up due to the sun. So there have been small ice ages, little ice ages that have occurred. And that's a lot of times it has to do with the fact that we're a little bit further from the sun, and we have actually had less solar output. So the sun's solar output does change over the course of many years. So climate does happen naturally. I want to stress that very important rule is that climate does happen naturally and happens through things like orbits of the Earth and of course of that of the sun. Now I'm going to go back to our presentation here. So I'm going to go here. And there's also things on Earth's surface that affect climate. And of course, one of the biggest ones is volcanic eruptions. This is Mount Pinatubo in the Philippines, one of the most violent eruptions in the last 100 years. Over 10 billion tons of magma and ash have been spewed out from this volcanic eruption. Incredible. There have been very, very violent volcanic eruptions. The last one, really drastic one, was during the Cretaceous extinction event, the Deccan Traps that formed as the subcontinent of India traveled across the what we call the Reunion hotspot, and that over time actually released a ton of ash and other things into the atmosphere, and all that ash and stuff almost created a blanket over our Earth and slowly cooled the Earth's temperatures down. So we do know that there are natural times where we have the release of ash that cools the temperature. Also during volcanic eruptions, we get a lot of carbon dioxide and other greenhouse gases that get shot up in the atmosphere that can also warm the Earth as well. And I'm sure a lot of you have heard of these gases like carbon dioxide, which we'll talk more about later on. But so as you can see, when we study climate and we look at trends in climate, there are natural processes, but that's not the whole picture. And you'll see in just a little bit later on that that truly is not the case completely. Now, so as I said before, I mentioned this whole thing called the Milankovitch cycle, Milankovitch cycle, excuse me, not Milankovitch cycle. And this is a study over the Earth's orbits and sun fluctuations and all these things, the precession. And as you can see here, the Earth goes through a fairly common trend in climate. Now, this is time in millions of years, so 800 million years, 700 million years, 600 million years. And you can see that normally we go up in temperature, we go down in temperature, we go up in temperature, and we go down in temperature. And these areas here are ice ages. These are interglacial periods. We actually are in an interglacial period right now where the glaciers are melting. They eventually the temperature goes back up, but then eventually it cools back down. We move into another ice age, then another interglacial period, a very hot time, and so on and so forth. But you'll see here as we get closer to modern day, things are not working the way that they normally do. And again, the recipe for climate has changed in the last, small period of our time in the last 100 years. Things have changed. And we're going to talk about some of those changes, some of the extra recipes that we're adding to the natural processes of climate. Think about you're building a soup, and as you make a soup, you add all your ingredients, but if you want to spice things up, you got to add some spice, maybe some sriracha sauce or some chili pepper or something. And believe it or not, that's what humanity is doing right now. And as I said, later on, we're going to see some really cool climate data that Mark has put together for us. Now, when it comes to studying climate, we have lots of different things. And again, Mark is going to show us some of the scientific data that in regards to some of these things. So I'm going to go over these very briefly. But one of the things that we can study with climate is we can look at ice cores. Ice is great for looking at history of the Earth in terms of its atmosphere. Why? Well, ice is actually different gases in the atmosphere dissolve in ices. And one of that is carbon dioxide. Carbon dioxide actually is dissolves in ices and actually traps that carbon dioxide. So if you drill through an ice core that's been around for a very, very long time, you can actually study the amount of CO2 that's been dissolved in that ice over those long periods of time. And again, I'm not going to go into great detail about that because we're going to have some really cool data that shows how scientists have actually measured those gases that have been dissolved in the ice cores. I'm a geology nerd, and geology can tell us a lot of the history of the Earth. Things get moved around on Earth because we have plate tectonics. The continents are moving, the oceans are moving, they're uplifting mountains and revealing ancient layers. We have found an uplift in Scotland that's revealing a 200-million-year-old coral reef. Now, when you think of Scotland, you don't think of coral reefs, right? But of course, you also don't think of things like that being so high up. Well, the climate was actually warmer back then, and we have evidence of that when we look at the different, we call strata of the Earth's rocks. So think of like a cake. The layers of the rocks tell us history. The different layers of that tell us the history of that time. The other thing we can look at is we can look at, again, that strata. Notice we have different types of rock. We have limestone, we have other things. And right here, this is actually a layer that has volcanic ash. And again, about 66 million years ago, there was a massive volcanic eruption that affected the climate. And we actually have that, what we call deposition layer, the deposits of that found here in this layer of strata. So you can actually see, if you were to pick out the samples in this layer, you can actually find evidence of volcanic ash and things like that. So you can actually look at the different layers of rock. Another thing you can notice is that if you take samples of these rocks and you find shells and clams and things like that, you know that maybe that area was once underwater. Maybe it was wetter back then. Maybe the sea levels were higher. Here in Florida, well, we had a lot higher sea levels. Actually, I'm going to go back to this picture here. This is actually a picture taken in Florida. Yes, it doesn't look like Florida, does it? But this right here is all marine life. If you were to pick up these rocks, you would find ancient seashells and things like that. And by the way, this was taken right near Gainesville. Yeah, for those that live in Florida, Gainesville is pretty much right smack dab in the middle of the state. And the elevation is actually pretty high for Florida. Now, Florida's elevation is not very, very high, but for Gainesville, it sits about 180 feet above sea level. So not a whole lot of issue potentially of getting wet there, right? Well, not really. Back during what we call the Eocene and the Miocene periods, about 50 million years ago to about 30 million years ago, this whole area used to have ancient marine life. So the climate was hotter then, it was wetter, the ocean levels were higher, and this area of Florida was completely underwater. So we can look at the evidence of climate by looking at stuff like that. Also, if you look right here, you can see this looks like a crocodile, right? It is. It's a fossil of a crocodile. We can use fossils. When we look for fossils all around the world, we can see what kind of animals lived in these different areas. Well, what if I were to tell you that this particular crocodile was discovered underneath the ice in Greenland? Now, you don't think of crocodiles in Greenland, do you? No, but during the Eocene period, about 50 million years ago, the temperatures were almost 6 degrees to 8 degrees warmer than it is today. There were palm trees in the Arctic Circle. There were palm trees near the North Pole, and there were crocodiles swimming around. It looked like the Florida Everglades at the Arctic Circle, which is crazy to think. But remember, the Earth could potentially end up like that. We could have Florida-like conditions in Greenland if the climate keeps changing. But remember, it takes millions of years for that to happen, not hundreds of years or even less than 100 years. So this is something that we are going to talk a bit more about, how fast we're accelerating the climate. Now, so those are some of the different ways that we can find and look at climate science. So what I'm going to do now is I'm going to go ahead and the most important thing when we're looking at climate science is we want to look at data. We want to look at the evidence. As scientists, we want to look at what scientists are observing, collecting all around the world, just like we saw here in those examples. And one thing we can do is we can do something in the planetarium that makes it really truly special is we can use our domes to show off some really cool climate science data. And that's why we brought Dr. Mark Subbarao in today. And so what we're going to do is we're going to have Mark here present you all some really cool, fascinating things. But before we do that, Justin, any questions from the audience so far about some of the climate science we've talked about already?
Renee had asked, where are the ice core samples taken primarily?
That's a great question. Mostly it's in Antarctica. That's where we have the largest deposition of ice over a long period of time. When we talk about interglacial periods, the polar regions tend to have the most ice. So we get a really nice long-term time to really look at the different types of gases dissolved in that ice.
Fantastic.
All right. So, Mark, I'm going to go ahead and turn it over to you, and let's take a look and see what you have in terms of showing off some cool climate science data.
All right. Thanks so much, Derek. That was really, really enjoyable to listen to. First of all, let me, so my job at the Adler is director of the Space Visualization Laboratory, and what we try to do is make data interesting and visible. Behind me is a visualization that we didn't do. This is done by a climate scientist named Ed Hawkins. I think it's one of the most brilliant visualizations because it's so simple and so beautiful. So what you're seeing is each line of color is representing the temperature in a year, and we have different ways of measuring the temperature throughout history, but at least since 1880 or so, we have very good, just direct measurements all around the globe. People are actually measuring temperature all around the globe. And so what you're seeing going from this side to this side is in blue, years that were colder than average, and in red, years that were warmer than the average of that time. And you see this very dramatic turn to the red towards my right. And that's of course, that's anthropogenic, human-caused climate change, and that's what we're concerned about. So what I'm going to do is, much like Derek did before, I'm going to switch over and show you some of the Planetarium software, and we'll dig into some of the science and some of the data that we're getting around this. So let me just take control over here. All right, and now you should be looking at the Earth.
There it is.
Yep. And it was, of course, this view of the Earth we didn't have till we traveled to space, and really not really until we traveled far into space with the Apollo missions. And it was the image from Apollo 8 of what was called Earthrise that really launched the environmental movement and the Earth Day that we celebrated yesterday.
Yes.
To me, the most remarkable thing is this gorgeous planet is how thin our atmosphere is. I mean, if you look at it, and this is tried, there attempts were made to do this as accurately as possible, you can barely notice that thin blue atmosphere. It's only 62 miles to the edge of space, right? I mean, especially with Florida speed limits, you can get there in 45 minutes, right? If you just had highways that went straight up, which unfortunately nobody seems to want to build. But when we think about all life on Earth, it's that thin atmosphere that makes it possible. And because it's so thin, that's one of the reasons why we actually are able to influence. And there's some other reasons as well that we'll get into in a little bit. But talk about climate, let's one thing that I think is helpful is to think about the ingredients that go into making up climate. So really, we are warm because energy and in the form of light, and that's what we're representing now with these little squiggles, comes into the Earth. from the sun. So we all living creatures, except for a few things on the bottom of the ocean, rely on the sun for our existence. When that light comes, some of it is absorbed by the Earth, but some of it's reflected. And we're going to show that now. It's about 37% of the light that's reflected, the energy in the form of light that's reflected. And that fraction, of course, is an important ingredient in our climate. So most of it gets through. The fraction that gets through is absorbed by the Earth, and it warms. It's mostly clouds and ice that do the reflection. It turns out that all things glow. The sun glows in light we can see, but the Earth glows as well. It just glows in a different kind of light. It glows in invisible infrared radiation. If we could see it, we'd see that it's coming off the Earth in all directions. And so there's this balance between the energy coming in and the energy going out. And we always meet that balance. And when we have that balance, if all the ingredients in that equation in the budget stay the same, the Earth will stay the same temperature. But much like your family budget, if say your income goes down or your spending goes up, things are going to change. And that's what's been happening on Earth. One of the things to keep in mind is this isn't just theoretical. We actually measure all of the ingredients going into this every single day. So I'm going to turn off some of these layers. And so if I want to look at the fraction of the Earth that the light that's being reflected, we have a map of that. I'm going to show you a map. This is a map over the last week of all the reflected radiation averaged over the last 8 days. Likewise, if I want to look at the radiation being emitted from the Earth, we can measure that. We have infrared sensors on our satellites. And this is likewise a map of all of the radiation, the infrared radiation averaged over the last week. And so there are regional variations, and those variations depend on things like weather, but averaged over longer periods of time, you'll get a more uniform. Let's talk a little bit more about this very thin atmosphere. As thin as it is, it turns out that most of what our atmosphere is made out of, which is oxygen and nitrogen, is completely transparent to this radiation that I was just showing. It's only sort of lopsided molecules that matter. So oxygen is in the form of O2, two oxygen molecules, that's symmetric. Nitrogen's in the form of N2, that's two molecules, it's symmetric. It's transparent to the radiation. But the next biggest component is carbon dioxide. It's a very small component to our atmosphere overall, but because it's unbalanced, the two carbons and an oxygen, it's able to actually trap some of this infrared radiation. And when we increase the CO2, we increase the amount of infrared radiation that we're trapping, we raise the Earth's temperature. And to a degree, that's a really good thing. If we didn't have this is the greenhouse effect. And if we didn't have the greenhouse effect, the Earth would be terribly cold. It'd be barely suitable for life. We need the greenhouse effect. The problem is that we've been changing this, and we've been changing it on a very fast time scale. So let's take a look at that. I'm going to jump you me jump you over to the area where I come from. So we're looking down at the Earth, and we're right above the Great Lakes. I kind of like sometimes to like put south up just to disorient you a little bit, like you're really in space. But these are the Great Lakes. The one we're zooming into is Lake Michigan, where Chicago is on the banks of. But I'm not going to head to Chicago. I'm going to head a little bit north of Chicago to a coal-fired power plant. This is actually a power plant that's it's one of the worst power plants in the region. It's quite old and quite polluting. And one of the ways that it's polluting is it's putting out carbon dioxide. Now, we've actually the levels of carbon dioxide in our atmosphere have been rising pretty dramatically, but it's a colorless, odorless gas. Um, it's not something you see or notice. We did a planetarium show with Dan Schrag, who's the director of environment at Harvard. And what he wanted to do was imagine, what if we could see carbon dioxide? Imagine that carbon dioxide glowed red. If that was the case, we would notice how we're changing our atmosphere. And so that's the experiment we're going to do now. We're going to now code. We see the carbon dioxide coming out of the smokestack, but we also see the sky tinted red. And what I want to do is show you this graph. So this is a graph. Let me straighten it out for you. This is a graph called the Keeling curve. It's probably one of the most famous plots in all of science. Charles David Keeling was the first person. Let me actually go. Hold on a second. I didn't mean to show you that. I've given you the the punchline. But he started actually in 1958 on the island of Mauna Loa on Hawaii, on the extinct volcano there, measuring carbon dioxide, which is a hard thing to do because we breathe carbon dioxide, right? So he would go out, walk away, far from anyone else. He would have a little glass vial that he had evacuated. He'd sort of stand into the wind and he'd hold his breath for a while, and then he'd open it up, fill up the air, and he'd make this measurement. And what happened was, as he made that measurement, he started to notice, so this went back to the early 50s, that the levels of carbon dioxide went up and down. And so those numbers that are on the y-axis, 310, 320, 330, those are parts per million. So the levels of CO2 in our atmosphere are actually quite tiny. And that's why you don't actually have to add that much to start to change the overall concentration. This up and down that he was seeing, we can think of that almost as the Earth breathing. Most of the land mass on the Earth is in the northern hemisphere. So in the summer, plants grow, they absorb carbon out of the air through carbon dioxide. The carbon dioxide goes down. In the winter, they decay and they release it back into the air. So the up and down that you're seeing is a natural cycle. But then as he went on and started measuring it more and more, he started to see on top of that natural cycle, those levels going up and up. And as we've continued to measure it, those levels have continued to rise higher and higher. Currently, we're now at about 414 parts per million. We think that in the pre-industrial age, we were somewhere around 280 parts per million. That's close to a 50% increase. We've dramatically altered the composition of our atmosphere. This is a simple measurement. I mean, people can argue about the cause for the increase in temperature, but you really can't argue with the fact that we've significantly changed the composition of our pull back away and look at our beautiful Earth. You know what I'm going to do next? I think Derek did a really good job of talking about timescales. And I want to just give you a sense of that, looking at some of the data from, in this case, actually an ice core like the image that Derek showed. So these ice cores are pretty amazing. The one we're going to show is the Vostok ice core. So this was a drilling that happened as a joint project between the Russians and the Americans. They drilled down actually more than 2 miles into the ice. This ice core is more than 2 miles long. And as you go down deeper and deeper, you go farther back in time. And this one actually takes us about 400,000 years into the past. And what you're seeing in this graph is the relative levels of carbon dioxide throughout that history. And when I play, what I'm going to do, I'm going to play this forward, and what you're going to see is how when CO2 levels are high, the Earth warms. We're going to see that actually in the sea level rise as well. Also, we're doing the same trick where we're tinting the Earth red depending on the CO2 level. So watch the graph, watch the color, and watch the Earth. And we're going to play this forward 400,000 years. Earth warms up. And then it cools down, the ice retreats, warms up. It warms up, the ice retreats. Sea level's doing the opposite of the ice. Now, if you look at the pattern of this graph, this actually looks a lot like some of the graphs that Derek was showing. Is that because at the core, a lot of this pattern is caused by these Milankovitch cycles with volcanism, which is kind of a random effect as well. So this kind of shows how much CO2 levels have varied over the last 400,000 years. Let's just take this a little bit forward to the beginning of the industrial age. So we're now at the year 1850. And now let's go to today. And so this is what we're seeing. That's that 50% increase in the level of carbon dioxide. The Earth has natural ways, something called the carbon cycle. It has a way to absorb carbon dioxide. That's why levels have gone up and they've gone down in the past. The problem is that the time scales that we're dealing with are just completely out of scale with these natural time scales to absorb the carbon dioxide. So let me project this forward to the middle of this century, and you see the levels that we think we'll be at. So we're looking at more than 500 parts per million. And it seems like it's really going to be hard for us to avoid this level of carbon dioxide, which will lead to some pretty significant issues.
Mark, we did have one question from Anita,
Yeah.
and she was asking, is 8 degrees really the factor that would turn something like Greenland into a tropical area? Can you go into a little bit more detail on how that temperature and the carbon dioxide levels can dramatically change a continent like that?
Yeah, so I'm not gonna 8 degrees on average. What you can do exactly is just add that to the temperature, because the weather is a pretty complex system, right? But Greenland probably will be okay if we have an 8-degree rise. It's the rest of the world that won't. even with the the kinds of things I was just talking about, it probably won't be as dramatic as what we saw in 50 million years ago in the Eocene, where we did have the entire world being tropical. There have also been times, if we want to go back even further, where the entire globe was frozen over. What we didn't have during any of those times was human civilization, um, and that's why this is so devastating. It's how fast it happens, um, and it's the impact of humans. So yeah, Greenland, probably what we've done so far, and what we'll do over the next, um, if we continue without reducing emissions, we're not going to make Greenland tropical, but we are going to make the tropics, um, and the subtropics, very much more difficult places. All right. Let's now project forward a little bit. One of the challenges is that it takes so long for the Earth to sort of naturally absorb this carbon. So, um, and we think that timescales is on tens of thousands of years. So what happens in the future, of course, depends on our actions. But if we take sort of a modest projection of where we might be in 10,000 years, it might look something like this. And here you can see um, the effects of sea level rise over that period of time. So the amount of sea level rise we've seen so far um, is not that significant, but it's really over these kind of timescales where we see, well, we have the potential to see some pretty dramatic changes to the globe. Of
So
course, that doesn't look too good for Florida, does it?
yeah, if you're a vampire and you can live forever, you might want to look into real estate out west. You know, to really get your bang for your buck, right? Um, but yes, I mean there are plenty of times which the state of Florida was underwater, as you saw with the fossil records. But Mark, in this data here, where you know, since we have a lot of viewers on Facebook that are coming from Florida, when does it really start to get really dramatic for our state? Are we able to go back in time again to see kind of the progression?
Yeah, I think to be honest, this is a longer scale simulation that doesn't really
Okay,
have the resolution to to
gotcha.
to say that. I think um, you know, the thing about Florida is you're so low, right?
Yeah,
Um,
we are.
but on the order, you know, I think, you know, obviously you've already seen some issues,
Oh yeah.
but on the order of a century, things could be looking pretty bad.
And,
Um,
and of course, you know, not just Florida, but most of our cities are coastal, you know, and not just in the United States, but all over the world. This is something that is very concerning because most of our global economic areas of the world, like New York and you know Tokyo and you know Shanghai and London. I mean, all these places are very close to the coastline that could severely be impacted.
yeah, so the question is like, what can we do about it, right? And one of the things that's happened um, pretty dramatically, and part of what's caused that increase is just the fact that the population has been growing. So this is a fun little animation. So just to show you the change in population from 1950 to today, what they've done is, or what we've done is put a dot where we've grouped together 1 million people. So each one of these dots represents 1 million people. And we'll kind of run this forward to today, and you kind of see the explosion in population. I can actually take this back farther if I want. Um, it's actually more dramatic, I think, if we go and look in Asia. Or, that's the difference, right? And if we project forward to the year 2050, that's only going to increase. We have more people. Every person's using more and more CO2. How do we solve that problem? And that's sort of the problem of our age. We have been seeing there are some hopeful signs. We've seen a really great improvement in our use of renewable energy. In solar energy, in wind energy have exploded by an order of magnitude in the last few years. But if we sort of far out their idea, which might be fun to talk about, but also has some pretty worrisome consequences, is one way we could potentially solve this problem in the future is through massive geoengineering, actually changing our climate on purpose, right? So in a way, we've been changing the climate of the Earth unintentionally. Could we do the opposite thing intentionally? And one idea is that you could potentially do that by doing something we were doing unintentionally before. So aerosols, if you probably remember, like chlorofluorocarbons and causing a hole in the ozone layer, that's actually one of the great environmental success stories, is that we passed laws, we banned them, and we've actually helped fix that problem with the ozone layer. It kind of gives us hope that maybe we could do the same thing with climate. But one of the interesting things, or maybe not interesting, but one of the unappreciated things is actually those aerosols actually had a cooling effect on the planet. They're actually helped reflecting more of the Earth's sunlight. And we've sort of lost that cooling effect as we've stopped polluting our air more and more. But what if we did this on purpose? What if we ejected aerosols? If we did it at the equator, they would quickly spread out around the globe. And they would reflect more and more of the sun's light, and actually we could use that to cool the planet. The problem is that the same aerosols also have negative consequences, potential consequences, and all kinds of them. So this is one of the real challenges if we want to look at these sort of massive, expensive planetary scale engineering projects. It could also cause a lot of problems, and I'll kind of leave it there. This is what we're facing. It's like we're now facing a pretty dramatic global challenge, and we've seen the world come together and dramatically change the way that we do our day-to-day lives. Climate's going to require the same type of response. The difference is that the virus needed us to act within weeks. Climate's going to require us to act for years and decades and into the future, and really change the way we do things. And that's the challenge.
That was wonderful, Mark. Thank you. I thought that was incredible to see all those visualizations, and it's just really cool, the technology we can utilize in the planetarium to really, because I think a lot of the issue with climate science is that people they hear these things in news clips and things like that, but they really don't know how it affects the overall thing. And by showing that kind of stuff and showing them in color changes and particles moving around, hopefully gives people a chance to visually see what science we're actually collecting about the Earth, and hopefully that can maybe help understand that, you know, climate is happening naturally. We know this, but we're also contributing to it. And what I'm going to do real quick here is I'm going to share another part of our presentation here, and I want to talk about that. You know, we've been mentioning carbon dioxide, but there are other greenhouse gases that are affecting our Earth as well that are kind of not mentioned a lot. You know, we have water, the Mickey Mouse molecule. Water vapor actually absorbs a lot of heat as well, and so does methane. And one thing that we're seeing with the melting of the ice, and especially the permafrost, especially in northern latitudes, is we're seeing a release in swamp gases like methane, which actually trap in 4 times as much heat as carbon dioxide. So this is going to be a runaway effect, which is really going to dramatically affect our ability to deal with this. So right now we're mostly focusing on carbon dioxide, but in reality, we have to focus on these other things as well, and how can we keep that from going on. So there's definitely a lot of science to it. My question is what are some solutions? Well, I figure we're planetarians, and we like to talk about space, and this is our chance to kind of explore space a little bit. You know, the idea is that what if we don't actually solve this issue, right? What if we we end up having to leave Earth? You know, Elon Musk and several other members of the Earth are saying, you know, maybe we should build colonies on other worlds. And of course, our closest cousin to the Earth is Mars. And, you know, we talked about Mars in one of our recent public shows. And Mars is a place where, unfortunately, you know, it may be the most quote unquote Earth-like planet out there. This is not really Earth at all. It doesn't have a magnetic field that protects us from solar radiation. It has the average temperature is, you know, it goes from 80 degrees to minus 150 degrees. It's a very inhospitable place. It's a place where, you know, we couldn't have billions of people living on Mars, because really the best place to live on Mars is going to be underground. They're all throughout the surface of Mars. There are underground lava tubes and caves and things like that where we could technically live. We have evidence that Mars was a water planet at one time. We see here with the what we call the Tharsis Plateau. There was an area right here called the Noctis Labyrinthus where we had water that would have drained down into these basins down here like the Valles Marineris here. But now Mars is no longer the Earth planet it is. So is this a solution? Is the idea of going to another planet a solution? Well, maybe for a small amount of our population, but really not so. But we're discovering exoplanets out there. We're discovering
Derek, do you mind if I just comment on that a little bit?
Of course.
Because this is one thing that I find really worrisome and irresponsible when you hear people like Elon Musk saying this. So, you know, to make Mars habitable is an incredibly, I mean, you can talk about the idea of terraforming Mars is something that could potentially in the far future be done. Whether or not that's a good thing. The scale, I mean, I said that we have a huge problem in terms of solving the climate crisis, but the scale of that is nowhere is something we can do. It's completely within our rate. It's nowhere near the scale of making Mars habitable. You can't even compare the two things. So like to think that that's a solution, it's much easier just to solve our problems by factors of thousands than to like make Mars Earth-like.
Exactly.
It's just not really a solution. But yeah, go ahead.
And even a wilder solution, some people say, well, eventually we're going to have to leave planet Earth. We're going to have to find another Earth. What if we really mess things up here on Earth? And the reason why I'm drawing all this in is to go what Mark said, is that it's so outlandish and crazy to think about that we can look back at all these things and what we learned in astronomy, how important our planet is for us. So I'm going to go to this little place called Kepler 452b. Now, of course, we have no idea what this thing actually looks like, but we know that this little object, a super Earth, as we call it, is found in what's called the habitable zone of this solar system. But let me tell you the distance of this object. It's over 1,400 light years away. Now, light is how far light, the speed of light. The light travels about 6 trillion miles or so, in a year. And a light year, if you take 6 trillion and you multiply it by 1,400, it's going to give you a very big number. So the chances of us leaving our planet to going to this is going to take generations and generations and generations just to get there. And the other thing we have to note is that even though this might potentially be an Earth-like planet, if it's bigger than Earth, it could have a lot. It will have a lot more gravity. It also we don't know what the atmosphere is like on this planet. It could have more oxygen, more carbon dioxide. It could have other gases that are toxic to human life. And so the point I'm getting at with this is that as astronomers, we can figure out saying, well, we could abandon Earth, look for other worlds, but really we are well suited for this place right here, our planet. Our planet is the best spaceship around. I mean, really it is. We have all the air that we can breathe, all the food we can eat, the water we can drink, all the unlimited Netflix we can watch after all this is done. We have a lot of wonderful resources on our planet. So the question I want to ask now is, I'm going to go ahead and stop sharing this, is we can really, as Mark was saying earlier, we can really solve our issues here on Earth. We don't need to go to another planet to solve it. We can do something here. We can geoengineer, as Mark was saying, or we can do other solutions as well, like work on building resources. We can use the power of the sun to help us by building more solar arrays. Solar energy is getting cheaper. It's getting much more abundant. We're seeing more houses using solar energy instead of, going net zero. And eventually the goal is to eventually get to the point where we don't have to use as much energy from a coal plant or a power plant nearby. And here, being that we're from Florida, why not show off what Walt Disney World's doing, right? This is the solar panel array that Disney's working on, hoping to get all their energy needs from this solar farm. So pretty incredible, and we can do this. And again, it's getting cheaper, more efficient. But there are other ways we can develop energy. If there are places where we get a lot of wind, wind turbines can also solve our issue with energy, because the most important issue with climate change right now is we're adding that sriracha sauce, that excess carbon dioxide, excess greenhouse gases that are affecting our climate at a rate that's just unsustainable for us. So how can we alleviate that? We build resources that don't release carbon dioxide, that don't release methane, that don't release all these things. And things like solar and wind can do that. Now, there are some negative effects of wind. One of them is that birds that travel through currents and wind currents might potentially get damaged by these wind turbines. So we're thinking of new innovative ways to help the motion of these turbines help alleviate those issues, or potentially install them in places where we don't see a lot of bird populations travel through. Now, if we're looking even further ahead into the future, we can go back to nuclear. I know the word nuclear has scared a lot of people. HBO just released the Chernobyl series, which is a fantastic series, and just showing that unfortunately, if you do things irresponsibly, you can end up with very, very bad consequences. However, there is another type of process we can use that is being developed today. That is nuclear fusion reactors. This is tokamak. This is a fusion reactor. It's a theoretical one. And unfortunately, at this moment in time, the amount of energy put into the system is still greater than the energy being outputted. Now, we want to flip that around. When the output energy is greater than the input energy, you have excess energy, and that's where you can supply energy out to the masses. But this is very clean energy, does not release any harmful stuff out there that will pollute our atmosphere. And unlike fission, which requires a process of heating water through plutonium and boron and all this stuff, and you get highly radioactive material waste, this, if the hydrogens fuse together to produce the reactions needed, and alpha particles, which are basically stripped hydrogens without an electron, they're basically sped up very, very fast. They react with each other, generating energy. this process doesn't work if it doesn't work. It doesn't have the meltdown effect that you have with nuclear fission, which is the one that we're currently using today. So there's actually very low risk with running fusion. So we need to invest in new technologies like nuclear energy, alternative sustainable energies like wind, solar, and things like that, hydroelectric. These are the things that we can build today that can solve our issues, because I'm going to be honest with you, looking at that planet Earth, as Mark said earlier, from when you flew, the astronauts that are above the Earth looking down, it is a miraculous place. It is a fantastic place, and it is the best spacecraft. And so we have ways to solve that, and that's what we hope that we can share with all of you today, that using this scientific data, using us as educators to help understand how our Earth is changing and evolving, how we as human beings can use this time to really solve our issues and make this place a better world. And so what I'm going to do now is we have a couple more minutes left. And Justin, any last minute questions or remarks from anybody from the comment area of the live chat?
Yeah, sure. Either for Mark or Derek, we had a question from Chris D talking about the albedo effect, and are there things on Earth, engineering, roads, and other situations where we can use this type of engineering to help affect the direction that we're going?
Yes, there are, right? And albedo's a very important thing. So we know, for example, that in cities are warmer than the areas around them. So the urban heat island effect. And that's just because they're absorbing more radiation. So when you think about rooftops, for example, if you green rooftops are an interesting project. You can think about things like parking lots, highways. So even having a lighter color highway as opposed to a dark color highway, it will reflect more light. Then all those things can have an effect.
So we're in this situation with COVID and lockdown, and how is that affecting the analysis of our pollution levels, our atmosphere? This has got to be a great benchmark tool for study for the future on the way we've dramatically reduced our carbon output over the last month that may end up going several more months. I got to imagine scientists are drooling over this data on how they can study it further and see where, how is COVID and this impacting us here on Earth.
Yeah, I think you've probably all seen these stories. In a way, it's probably even more dramatic with some of the other forms of air pollution. Look at smog levels in certain areas. So, I was in India last fall, and in some of those major cities, people haven't seen blue skies in years. It's really, in some of these Asian cities, just the level of smog is so bad. And now they're having blue skies for the first time in decades.
It's absolutely astonishing. Yeah, I mean, and even in the United States, places in the West Coast and even in the Northeast are seeing dramatic drops in pollution. Here in Florida, without all the shipping going on and all that, and cruise ships and things, they're seeing a remarkable reduction in algae blooms, and the water is so much clearer. There's a friend of mine who works at the Canaveral National Seashore, and they're finding out that they're actually monitoring a huge resurgence of sea turtles because they're not dealing with all those issues. However, there is one negative effect in terms of the environment, since this is Earth Day or Earth Week. We are noticing, though, unfortunately, with everybody wearing those gloves, we're seeing a lot of pollution with people dumping gloves into the ocean. So now we're seeing people dumping masks and gloves in the ocean. So we really have to be cautious about what we're doing to our planet as well. But I think the overall effect, though, is really, I think, helping us really show that pollution and carbon emissions and stuff is having a great effect on our world, and with less driving, less all that stuff.
So, I just I'll add one thing. The sort of difference with the carbon dioxide levels as opposed to, say, the smog is that it just is lasts in the atmosphere so much longer. So if we think about where we want to be, where we want to be to, like, keep ourselves to 2 degrees C, the title of this, we really need to get to the point where we're reducing our CO2 levels by about like 7.5% every year, our emissions. Projections I've seen, given who knows what's going to happen in the coming months, but we're going to globally, our CO2 emissions will go down by 6% or something. So we're kind of on pace by meeting our requirements this year, except we have to do that every year, and every other year we've been increasing. So this is the kind of change in behavior but it needs to be sustained, because it's tens of thousands of years that CO2 will remain.
And one of the questions we get a lot at the planetarium, and Justin, let me know if you have any suggestions as well to add to this, is we get people to say, okay, yes, what is one person can they really do to help with solving this climate issue? Because some people, I do really feel like that they feel like, well, there's really nothing I can do. But what is something that can be very helpful for encouraging people to help combat that number, to help keep that number down, and so we can get below that 2 degrees, which is the tipping point? Mark?
Yeah.
Yeah.
No. That's always a really hard question, because in the end, all these things that require collective action require everybody to do it, but your individual part can only, you can only do so much. Sometimes it's very frustrating as you're taking all these actions. You see people around you not doing the same. Catherine Hayhoe is a climate scientist and wonderful public speaker. And I really encourage. She's got some great videos online. You get a chance to see her TED Talk or something. I highly recommend it. But she says something really interesting, which is the most important thing we can do about climate change is to talk about it. So it's great, all of our individual actions, LED light bulbs and don't drive as much and buy a more fuel efficient car next time. But the most important thing for us to get to the point where we're, as a global society, meeting this head on, is for everyone to be aware. That's why education and talking to your neighbors and convincing them that it really is a problem. And I think that's how we solve it. We went to the moon. That was a huge challenge. We had everybody stay home in a month, and we're dealing with this challenge now. We can do this as society. We know that we can. We just need to get on board.
That's great. I have one other question, and Justin, we'll take a couple more. I wanted to talk about real quick, Mark, about, have you had any positive responses from your planetarium programs with this climate science data you've shown? Because you said talking about it is important. And as science educators, our job is to talk about it. And have you had any very good positive responses of showing these things you showed us just a few moments ago?
Oh yeah, absolutely. Of course, the best times, and they're rare, are when you have somebody who was a skeptic who suddenly starts to think differently about things. I think the problem is that we've gotten to this point where we've turned what is really a scientific issue into a political issue. And as much as we can remove that, and that's why I like being in a planetarium, it's like, let's just lift ourselves off the earth. Let's forget about like where we are, what we are, and take the bigger view of things. So I think the other thing that you can do, and the advantage of our spaces, is really sort of surround people and things, because a lot of the information you get, well, one of the challenges was really like a lot of the climate change information is graphs, and we have kind of a rule, right? I know, like Derek, probably, like, people say, don't ever show a graph in a planetarium, right? Like, we avoid it like the plague. It's like, how do you show graph-like things in that immersive space? And there's some fun ways, I think, to get that across, and in a way where we can take things that often we have to ingest out of context and put them in context. So we can see it in the context of the Earth. We can see it in the context of the motion of the Earth around the sun and the seasons and the time scale. In astronomy, we're used to dealing with big scales. We deal with them big physical scales, but we also deal with these huge time scales. And that's, that's the other thing, something you kept stressing wonderfully, which is that, yes, the Earth changes, it gets hotter, it's been colder, it will be again in the future, but never has changed so quickly. And that's really what I think we can convey by putting things in its context, both in space, looking at Mars and looking at Venus, looking how they've dramatically changed,
Right.
And also by looking at back and forward in time.
Great. Thank you. So Justin, do we have any last minute questions from the group, from the chat?
No, that's it for questions. If Mark, if you want to plug anything that you're doing over there at Adler, or you want us to post anything in the chat so people can find more about what you're doing and the science you're doing, we can make sure that they can follow you.
Sure. Yeah, you can just check out our website at www.adlerplanetarium.org. You can follow me on Twitter if you want, at Mark Subbarao. Not that I tweet that much, but mostly what I'd like to do is invite everyone, if you happen to make it in Chicago and back when we're back to normal and things are open again, I encourage you to come down and visit, and maybe you can join me in the visualization lab. We can talk about some of this stuff.
That'd be wonderful. I've been to Adler several times, and I love every time I experience it. So I encourage all of you, and it's just a wonderful time to share our. Even though this is a terrible time for everybody, it is also the silver lining is a wonderful time to collaborate with our friends in the community, and we're just very happy to be able to share with you all some wonderful people that have worked on all kinds of incredible things. And once this is all over, I hope that all of you get a chance to visit Mark and the other amazing team members of the Adler Planetarium up in Chicago. So I want to thank all of you for attending our virtual public show this week. And next week, Justin, you want to plug what we're doing next week? Because it's all about you, my friend.
Sure. Well, next Thursday, we'll be going into a little bit more about some of these spacecraft behind me here, a show called The Final Frontier, where we're going to be looking at the history of spaceflight, what we've done, and where we're going. So tune in for that next Thursday. And then don't forget to plug tomorrow night, because it's kind of Earth Week weather related.
Yeah, we are doing every Friday at 9 o'clock, we do our virtual star party. And unfortunately, the weather isn't going to cooperate, but that's the theme of tomorrow's program anyways, is about how we look at forecasts, how we deal with weather patterns. And one of the interesting things is that our other colleague, Frank, has actually taken many years of data collected by pilots in cloud cover, and actually has looked at how cloud cover in Florida has changed due to climate. So this might be something that maybe, Mark, you and I can work on, and as a science visualization, show cloud cover and how it affects astronomy.
Oh yeah, that'd be cool.
That'd be kind of neat. So maybe we'll collaborate on something for the future.
Yeah, sounds great.
So definitely tune in that as well. And so with that, again, thank you all for visiting. Thank you again, Mark, for joining us tonight. Really appreciate that. And we hope to see all of you again tuning into our programs and to any of the programs that Adler is putting on or any other planetarium in the world. And with that, thank you all for coming out. And we will see you next time, everybody. Thank you so much.
Thank you.
All right, everybody. Bye-bye now.